Hello everyone, we are Jessica Vila, Medardo Vivanco, and Mateo Roca, and together we'll explore how functions change over time. Thank you for joining us as we divide in an average and instantaneous rate of change, core tools in science and engineering. The rate of change, also called the ratio of change, is a measure that indicates how one quantity varies relative to another. In mathematics, especially in calculus, it represents the rate of change of a dependent variable relative to an independent variable.
E equals f of x. The average rate of change between 2 points, x sub 1 and x sub 2, is calculated by taking the difference in the function values, that is, f of x sub 2 minus x of x sub 1, and dividing by the difference in the x values, x sub 2 minus x sub 1. In plain English, you measure how much goes up or down on average for each single unique step in the across the interval. Why it matters? Well, this gives you a simple number summarizing the overall trend of the function. On that strange, just like saying my average speed was 15 miles per hour. Even if you speed up or slow down along the way. The next I'm gonna talk about the change rates. Instead of writing out f of x 2 minus f of x over the x 2 minus in every time, we shorten it to delta e over delta x. Here delta equals to f2 x 2 minus and delta x is equal to x2 minus x1. This compact phrase makes it crystal clear that we are looking at the total or global change in E relative to x over the interval. Delta E over delta E, where delta E is f of x 2 minus f of x1 and delta x is x2 minus x1. You can think of planning a road trip and you calculate your overall average mile per hour from the start to finish, ignoring the moments you hit traffic or spend on the highway. Delta E over delta x does the same for any curve, gives you the big picture slope. Well, this instantaneous rate of change. To find the rate of change at a single exact point x, we imagine making the interval between x and x plus a tiny bit called delta x shrink smaller and smaller until it effectively zero. We then look at f of x plus delta x minus f of x divided by the same. Tiny delta x, the value that is fraction approach as delta x goes to 0, scale the derivative at x or f prime of x. The limit as delta x approach 0 of delta e over delta x equal f prime of x. Well, why it matters? This is like checking your car speedometer at an exact second instead of averaging across the world trip. It tells you instantaneous rate which is changing with respect to x right at that point. In physics, for example, it converts a position time curve into an exact velocity at time t.
Variable exchange rate expansion for the function y equal x2. The rate of change is constant. Its derivative, the x equal to x, give the exact slope at h x valued as x increase the slope of the parabola grows linears. This rate shows E equals x squared, its rate of change varies because the derivative to x increase with x. For example, at x equals the slope is 2 at x equals to its 4. You know that the slope change point by point helps you predict how fast a quality accelerates or decelerates. Variable exchange rate expression. When x equals 0, the rate of change is 0 and the curve is flat. For x max 0, that derivative is positive and growing, so the curve rises increasingly steep. For x max 0, the derivative is negative and decreases, so the curve falls and step downward. At x equals 0, slope is 0 if x is positive, slope is positive and rise. If x is negative, slope is negative and grows steeper. Identify where slopes are positive or negative and how they change lets you understand when a system is speeding up or slowing down. The red dotted line on the graph at the center is touched 0 and the median to the right is about 0. The curve goes up faster. This red dotted line marks the derivative. Left of center is negative, showing a downward slope, and the axis is 0, marking the median. Right of center eclipse above 0, meaning an upward slope. Overlaying the derivative of the graph makes it easy to send exactly where all you the function beyond shift.
Real applications. These rate of change aren't abstract. They power it or measurement across field. Spoken form. In physics, velocity is change of positions over time. In economics, we track income growth or inflation rate. In medicine, heart rate is beat per unit and drug concentration change in blood. In engineering, temperature, pressure, or voltage shifts per seconds drive systems design. Why it matters? Since these applications proves that mastering rate of change unlocks insights in every discipline, from forecasting markets to designing structures. Conclusions. Understanding the rate of change makes it possible to analyze and predict dynamic behavior in field. It is the bridge between pure mathematics and real situations. Knowing how to interpret and represent it graphically is essential for solving problems in science, technology, and everyday life.